Alrighty, so here we are back with looking at these problems. And let's move on to this one. It says in the diagram below, a wire loop moves with initial velocity v naught to the right. For each lettered position determine the direction of the change in flux, the direction of the induced current. Add the current to the diagram, indicate all lengths of wire that have a current, the direction of the force in the segment of wire, the direction of the acceleration, if any, in the loop, and is the exiting velocity v greater than or equal to or less than v naught. So what's going to happen when this thing hits this magnetic field? And so we kind of have that sketched out in the notes here also. So looking at this, first of all, let me point out that if we look here, here, and here, these don't have, here, let me get rid of those. These don't have any magnetic field at all. So there is no magnetic field here. There's no magnetic field here. So right away, this is a region where there is going to be zero magnetic field, so there's no change in flux, so there's not going to be any change in velocity for these. And so the next thing we want to look at is what's going on for the remaining three. And what I want to talk about first is to point out that an induced current is only going to exist if the magnetic field is changing. And so if we look at this one, where it's entering the field, and this example where it is exiting the field, there you would have a magnetic flux change. When we are in the middle of the field, there is no change in flux. And so this would be another region in which there is simply going to be no current, no induced current, no change in magnetic flux at all. I kind of like to compare this with, if you imagine yourself like walking up to a pool. As you walk up to the pool, you're comparing yourself walking up to the pool either dry or wet. And as you walk up to the pool, as you approach it, you're still dry. So there's no change in dry or wet. As you dive in from when your fingertips first touch the water to when you go in and in and in up until your big toe goes under as well, if you dive in, that's what we'd be talking about here. You'd be transitioning from dry to wet. If you swim to the other side of the pool, like as an example here, you're not getting any more or less wet, right? You're just in under the water. So you're not changing that effect on you. And then as you exit the pool, you're going from wet to dry, and that's a change. And so we'd have a change in flux here. Similarly, and then here you're just walking away, you're not getting any more wet or dry. So either way, that's why we ignore the far left, the center, and the far right. We're looking at the other two. If we look at this hoop, as it enters the field, we're getting more and more flux into the loop. And the reason that's happening is because the loop is entering a field that is directed into the page. And so if it's directed into the page, we're getting more and more flux into the loop. And the way to oppose that is to have some come out. So if I imagine grabbing this bottom portion of the rectangle here with my right hand so that my fingers come out, that induces a current that is going to run this way. That's the direction your thumb will point. And so if we need to have some come out, that's why we have circles here. And then the effect of that is to have an induced current that's going to run this way. So with that much said, if we want to know the force, then we would take our right hand and point it in the direction of the current this way. The magnetic field is into the page. Your right hand points to the left. Same thing here. You point your fingers this way, and your right hand points into the page because that's the direction of the existing magnetic field. So your thumb points down, and likewise here, if you point to the right, you'd have a force directed up. The reason I don't have any force arrows drawn here on any of these portions is because there's no external magnetic field. So when you do the right hand rule, that's when your hand is flat, there'd be no force here because there'd be no B field here. And likewise, when we're exiting the field here, we talk about having less and less flux going into the loop. So you'd have to grab it with your right hand. Again, imagine grabbing this so that your fingers point into the page and your thumb's going to point this way, this way, this way will be the current. And the force would be directed down. Here the force would be directed to the right, and here the force would be directed upward. So the up and down cancel, the net force is to the left. So for these two, we'd have a force to the left and a force to the left. Those are the only two forces acting on it. So this loop would slow down as it enters and then exits the magnetic field.